This is the first in our series of video lecturettes to supplement the readings for Business Statistics, Business 226 for Spring 2013. The first subject that we're going to cover is the definition of measurement. Keeping it simple, the basic definition of measurement is determining the numerical dimension, capacity, or amount of something. In practice, it gets a little bit more difficult, however, a little bit more complicated. First distinction made in the text is between qualitative and quantitative measures. Qualitative measurement is when things are sorted into exclusive categories, but the categories have no natural order. You can sort dogs, for example, into different breeds, but the order of the breeds is arbitrary. Whether you have Labradors or Poodles at the beginning, in the middle, or at the end of the list of breeds is arbitrary. Until you specify some characteristic of dogs that can be meaningfully expressed numerically, something like weight, or how fast they can run, how long their hair or tail is. There is no natural order. If you sort breeds by color, there's still no natural order, and the process is qualitative. You can even give numbers to things, like geographic areas that are given zip codes. When you're only using numbers as convenient identifiers, it's still just a qualitative distinction. Once you assign numbers to things to reflect the natural order, natural dimension of whatever you are measuring, it is qualitative measurement. Physical dimensions, such as height, weight, and length, are clear examples when larger numbers always mean the thing being measured is taller, wider, or longer. And smaller numbers always mean it is shorter on each dimension. There is a natural order that is reflected in the assignment of numerical values. The second distinction that can be made is whether the measures are continuous or discrete. A continuous measure can include a fractional or decimal part. When you're filling your gas tank on your car, for example, you're not limited to just buying 1 or 2 or 3 or 10 or 15 whole gallons of gas. You can buy 7.5 gallons, or you can buy 12.13 gallons. The measurement is continuous. It can take on fractional and decimal values. When you go to buy milk at the grocery store, however, you have to buy 1 or 2 or 3 quarts or gallons of milk. You can't buy 4 3/4 gallons or 2.137 quarts. I like to say that the difference between continuous and discrete is like the difference between pouring cement and laying bricks, to use a couple concrete examples. I hope you get my little joke, but let's move on. There are 4 levels of measurement. Nominal measurement is the first and lowest level. And it's called nominal because it applies only the characteristic of identification or name that characteristic of numbers, that each number is unique. The fact that each number is unique, it can be used like a name. Room numbers, for example, use that nominal characteristic of numbers only. Just because a room has a larger room number doesn't mean the room is larger. It's just a different room. Nominal measures are essentially the same thing as what we just talked about that we call qualitative measurement. Now, ordinal level measurement is the second higher level of measurement, and it's called ordinal because it applies the natural sequential aspect of the number system. If you make a list of all the students in the class from the tallest to the shortest, each person is listed in place to reflect that they're taller than the person who precedes them, and they're shorter than the person that follows them in that sequence. But we don't know how much taller or shorter they are than those people or anyone else. We don't know how much taller or shorter the first person is from the last person, whether there's only a few inches of difference, or the tallest person is 6'8" and the shortest person is 4'10". We don't know that aspect. We don't know what the interval between the measurements are, simply the ordinal dimension. Now, interval is the third level of measurement, and it's called interval because it's based on some defined unit of measurement, such as miles or pounds or calories. We know the difference between 2 miles and 3 miles, or 20 miles and 30 miles. We know that the difference between 20 miles and 30 miles is exactly the same as the difference between 80 and 90. We know that the difference between 2 and 3 and 5 and 6 is exactly the same. The interval allows us to determine the difference between different things that are measured according to their place, their value in the numbering system. If the Biggest Loser in the TV show loses 250 pounds, however, we don't know what percentage they lost, because we don't know the ratio of their weight at the beginning and the end of the show. Ratio is the highest level of measurement. And it's called ratio because it's not based just on having a defined unit of measurement, but also that the system of measurement has what's called a true zero. That means there are no negative numbers. Nothing is less than 0. 0 is as low as you can go. Now, Fahrenheit temperature fails this test. Negative numbers such as 5 degrees below 0 or 50 degrees below 0 are often reported in certain climates in the world during winter. That's because 0 Fahrenheit is not true 0. Because there is not a true 0 in the Fahrenheit temperature scale, we can't say that the ratios hold true. That is, we can't say that 100 degrees is twice as hot as 50 degrees. By comparison, the Kelvin temperature scale is regarded as having a true 0, defined as the lowest possible temperature at which all molecules have the least amount of kinetic energy. absolute zero on the Kelvin scale equates to minus 459.67 degrees Fahrenheit, or 273.15 degrees centigrade. On the Kelvin scale, no negative numbers are theoretically possible. It is that point of zero kinetic energy. We can say then, in Kelvin, using Kelvin scale to measure temperature, that 100 degrees Kelvin is twice as hot as 50 degrees. There's twice as much energy. Fortunately, in most cases, it is not difficult to define true zero. With physical dimensions like distance and concepts like time, it's easy to define what true zero means and to measure things at the ratio level. Whether our data comes from a sample or a population is also important. Population data includes every case that meets the definition of the population. For example, all students enrolled at FRCC are a population. All the students in this class are a population. A sample is a subset of a defined population. And we can randomly draw a sample of 100 or 500 students from the population of current students enrolled at FRCC. Now, a sample doesn't need to be drawn randomly. You could consider the first 10 students that come in the door in the morning as a sample of students attending FRCC. It would not, however, likely be a representative sample. It would be a biased sample that is not representative of all the students at FRCC. To have confidence that a sample is representative of the population from which it's drawn, every case in the population has to have an equal chance of being included in the sample, and the sample must be drawn randomly. Now, a population can also be regarded as the sample of a larger population. We can say, for example, that the students attending FRCC are a sample of the students enrolled in the Colorado Community College system of 13 colleges around the state. However, some of those colleges are in rural areas, some are in metropolitan areas, some are large, some are relatively small. The sample of students attending FRCC probably isn't very representative of a sample of students for the entire system. Now, all these concepts about measurement are important because different statistical methods use different types of data. Let's look at the difference between descriptive and inferential statistics. Descriptive statistics describe what are called the parameters of a population. The average age of people in the United States is a parameter. The percentage of students at FRCC who are males and the percentage who are females, that is a population parameter. Inferential statistics, by comparison, involve methods used to draw conclusions about probability population parameters from data based on a sample of the population. For example, we can calculate the probability of the average weight of all newborn babies in the United States is within a specified range using data from a random sample of babies. Not measuring every baby, but estimating what the population parameters are from the sample. We can calculate the probability that babies born in rural areas are healthier than babies born in urban areas by using what are called inferential tests of statistical significance. Again, comparing data from samples of babies from rural and urban areas. Not just as if we had the data on the entire populations, we'd know for sure whether one group of babies is healthier than the other. Inferential statistics draws conclusions about populations from data based on samples. I don't want to get too far ahead of us right at the outset. We'll learn more about these methods in coming weeks.